Hey guys, so today we're going to do elimination reactions. In an elimination reaction, you eliminate something, which means you remove something. The second thing you need to understand is that we start off with a saturated organic compound and end up with an unsaturated organic compound. Saturated organic compounds have single bonds, S for single, S for saturated, and they can either be alkanes, haloalkanes, or alcohol. And your unsaturated organic compounds have double or triple bonds. If it's a double bond, it's an alkene. If it's a triple bond, it's an alkyne. How will you remember this? You will learn this mnemonic, simply undo. S for simply, S for saturated, U for undo, U for unsaturated. Now, what is it to undo? If I scribble something on the screen and I hit the undo button, it will remove whatever I just wrote. And in an elimination reaction, you remove stuff. So that's why that mnemonic is apt for this situation. Let's start off with dehydrohalogenation. Let me erase all of this. So the word de is Latin for off. Well, it's not a word, it's a prefix, but it's Latin for off. And it means to remove. So whatever comes after the prefix de indicates what has to be removed. And here we have dehydrohalogenation. So we know we have to remove a hydrogen and we have to remove a halogen. Now, what do we start off with? We know that we have to start off with a saturated organic compound because it's simply undo. And that means it can either be an alkane, a haloalkane, or an alcohol. But if we're removing a halogen, the reactant has to contain a halogen because you can't remove something if it was never there to begin with. And alcohols don't have a halogen. Alkanes don't have a halogen. So how can we now remove a halogen that isn't even there? Which means we have to start with the haloalkane. And we're going to add something. What are we going to add? I'm going to explain. So if you're walking on the street and a 4-year-old boy tried to steal something from you, to steal is basically to remove something from someone wrongfully. So this little boy is trying to remove your wallet from your purse. The chances of him succeeding are quite low because he's weak. But if a really buff man or woman in their prime, very muscular, tried to now remove this purse from this wallet from your purse, the chances of them succeeding are higher because they're strong. So we know that in order to succeed in removing something from the haloalkane, we need something strong, like a strong base. Now, some of the strongest bases contain an OH group. OH means a hydrogen bonded to an oxygen. So that's how you know you're going to use sodium hydroxide. Now, how I remember it is if someone really strong pushed me or shoved me really suddenly, I would say, oh. If I was feeling polite that day, I would say, oh. I would scream, oh. And your strong bases contain this OH group, which looks like the word O in uppercase letters. So that's how you're going to remember that base has to contain an OH group. Because you can also use potassium hydroxide or lithium hydroxide, but it has to have that hydroxyl group. And you're going to end up with an alkene plus salt plus water. So we know that alkenes have double bonds, and this means that they're less stable than alkanes. They're more reactive and they're weaker because of their carbon-to-carbon pi bond. So because they're weaker, it means that they're more prone for bad things to happen to them. I think of this alkene as a person. Now, because it's so reactive and so weak, going out during the pandemic means that it's more likely to get sick. So this poor alkene has gotten sick, and one of the symptoms of COVID is a sore throat. So people have told this alkene that it needs to drink salt water or to gargle salt water because salt water helps get rid of bacteria and it helps reduce inflammation and redness. So yeah, this sick alkene is now drinking salt water to get rid of that sore throat. So that's how you're going to remember it. And the way you write the salt is going to be as follows. You're going to write it like this. But the halogen here, you have 4 halogens: bromine, chlorine, iodine, and fluorine. The halogen that you use here depends on the halogen that is present in your haloalkane, because you can't suddenly come up with something you never had, like I said. So if you have 2-bromobutane as your haloalkane, then you would use sodium bromide. But if you have like something like 2-chlorobutane, I just want to make sure that you guys know that there is in fact a line there. When you write it out, you have to have a line there. If you have something like 2-chlorobutane, then you wouldn't use the same salt. You would now use sodium chloride. So just remember that those two things have to correspond. If it's not corresponding, you've done something wrong. So yeah, and then you're going to add water, and the chemical formula for water is just H2O. There are 2 reaction conditions for dehydrohalogenation. I'm just going to write RC for reaction conditions. I think there are 3 of them actually. So you need to use a concentrated strong base, as I said, which would either be potassium hydroxide, which is KOH, or lithium hydroxide, or sodium hydroxide, as I've used here. So concentrated strong base, dissolve in ethanol. What is ethanol? Ethanol is an alcohol, and the functional group of an alcohol is this. Contains an OH group. So you know you need to be strong in order to remove the halogen and the hydrogen from the haloalkane. And if you're dissolving in an alcohol, the alcohol contains this OH group. And if someone strong pushes you, you're going to say, oh. So that's how it corresponds with the whole idea of using strong stuff to basically succeed in removing the halogen and hydrogen. And your last reaction condition is that you need to heat strongly under reflux. So in all 3 of these reaction conditions, you are expressing the characteristics of someone strong enough to remove something. So just remember, it's heat strongly, dissolve in ethanol, which is an alcohol, and concentrated strong base. Dehydration, sorry. Dehydration is the exact opposite of hydration. If you haven't already watched my addition reactions video, please watch that, because it's the exact opposite of elimination and it will help you understand. So in dehydration, remember I told you the word D means to remove, and hydration or to hydrate means to add water, to drink water. So D, remove, and whatever comes after it is indicating what you remove. So that tells us that we need to remove water. But I'm just quickly going to show you what happens in addition reactions in hydration. I'm just going to write add in brackets so you don't think it's part of elimination. Because if you understand that, you'll be able to do this. So in hydration, you start off with an alkene. You add water. And you get an alcohol. I explained that we look at the alkene as a person, as we always do. And in this example, the alkene has gotten very drunk. Very, very drunk. And they're now drinking all of this water so that they can avoid throwing up. Because if you drink too much alcohol without water, you throw up, which is what we see in the movies. And this arrow over here is basically the alkene pointing to the alcohol, saying this is the culprit. This is why I have to drink all this water. The addition sign shows that it's going in. This is why I have to drink all this water. It's because of the alcohol. So that's hydration. Dehydration is the exact opposite of that. So the opposite of that would be to begin with alcohol and to get an alkene plus H2O. There are 2 reaction conditions. The first one is to use a concentrated strong acid, because we need to be strong enough to remove something. And the 2 acids we can use are sulfuric acid, which is H2SO4, or phosphoric acid, which is H3PO4. When you write these catalysts, please write them on top of the arrow. On top of the arrow, so it's going to go here. I just didn't write it because of space. But when you write the catalyst, you have to write it on top of the arrow. But anyway, you're going to use that. And then your second reaction condition is to heat strongly. Because when we heat something, we apply pressure so it can undergo a change. And it's strong. You want to be strong enough to remove something. Lastly, we're going to do cracking. Cracking, I feel, is the hardest. But we'll get there. In cracking, you begin with an alkane. Or not just an alkane, you begin with a longer alkane. And you end up with a shorter alkane plus a shorter alkene. Or you can get an alkene plus a hydrogen, but I'll get there. So now I'm going to explain this to you. If you have a vase in your house and it's on a table, my drawing is quite terrible, but bear with me. So this is the vase. And you drop this vase. As it hits the floor, it's going to begin to crack. And it will then shatter into many pieces. So this is still the same material. Like the porcelain or whatever was in this vase to begin with will be present in the broken pieces. It's the same thing. It's just a smaller version of it. Because you started off with something that big and you ended up with something this small. So cracking is basically making a smaller version of something. So if you started off with a longer alkane, you have to end up with a shorter alkane. But you don't stop there because remember, simply undo tells us we have to start off with a saturated organic compound and end up with an unsaturated organic compound. I'm not sure if I mentioned this earlier, but in the South African syllabus, for our unsaturated organic compound, we only ever use alkenes. I haven't seen them using alkynes. So because that has to be present somewhere, we know that we have to use an alkene, and it has to be shorter because we've cracked it. Now, the other type of cracking that you can have is where you start off with a longer alkane, as always, and you end up with, a shorter alkene or alkenes. Plus 2 hydrogens. So how you'll remember this is I link it to hydrogenation because the one up here is thermal cracking. This is thermal cracking. This one over here is catalytic cracking. Or at least from my understanding it is. Because catalytic cracking can be compared to hydrogenation because you use the exact same catalyst, but I'll get to that. Don't stress. So we start off with a longer alkane and we end up with alkenes plus H2. How you're going to remember this is, first you have to start off with your saturated compound and end up with unsaturated because simply undo. Then you're going to remember this in the following way. So when I was little, if I broke something very expensive of my parents, or if I cracked something very expensive that belonged to them, I would get a hiding. Not a bad hiding, but I would get a hiding. And for the purposes of this example, let's say you won't only get one hiding, you'll get 2 hidings. Hiding as in beating. One from your mom, and one from dad. So because you cracked something, because you broke something, you need to get 2 hidings now, or you're going to get 2 hidings now. H for hydrogen, H for hiding, and I explained why you get 2, one from each parent, or one from each sibling, whatever it is, however you want to remember it. And we have 2 types of cracking. One is thermal cracking. Thermal means heat. Just remember that. Add this to your vocab. Thermal means heat. So if it means heat, the reaction conditions are going to be as follows. High heat and pressure. Because we need to exhibit some form of strength in order to remove something from the alkane. And exerting pressure is showing a form of strength. It also has no catalyst. In catalytic cracking, we do use a catalyst, because the word catalytic is associated with a catalyst. So here we use low heat because it's the opposite of thermal cracking with regards to heat, because in every other type of elimination reaction we always use high heat, in dehydrohalogenation, in dehydration, and in thermal cracking, which is literally saying heat. Only catalytic cracking do you use low heat, but you still apply pressure because we need to exhibit some form of strength in order to remove something. And lastly, you use a catalyst. Why? Because it's catalytic cracking, so it's telling you we have a catalyst. And the catalyst will either be platinum or lead or nickel, but not all three. So I like to compare catalytic cracking to hydrogenation, because in hydrogenation you start off with, how do I make space here? In hydrogenation, you start off with an alkene, because you start off with something unsaturated and end up with something saturated. So you start off with an alkene and you add 2 hydrogens. In catalytic cracking, you end up, so this is your reactant in hydrogenation. In catalytic cracking, your product is an alkene plus H2. So you can see they're connected. And the catalyst that you use in catalytic cracking and the catalyst that you use in hydrogenation is exactly the same. So if you remember that they're connected, then you won't have to remember the catalyst for both. I hope this helps you, and good luck with your test.